One of the most important aspects of the study of chemical reactions, other than predicting their feasibility and the extent to which they would proceed, is the time taken for their completion. That is, the rate of a chemical reaction. Let us understand this in detail. In our daily lives, we see various chemical reactions taking place. For example, the rusting of iron in the presence of humid air and the combustion of butane, the main component of LPG. While the rusting of iron is a very slow process and may take years, the burning of butane is instantaneous. There are some reactions which take place with a moderate speed. Photosynthesis is an example of a moderate reaction. Have you ever wondered why some reactions are slow while others are fast? Chemical kinetics is the part of physical chemistry that studies reaction rates and explains why certain reactions are instantaneous and others are not. It also describes the conditions by which reaction rates can be altered. Let us start with a simple definition of the rate of a chemical reaction. The term rate is often used to describe the change in a parameter that occurs per unit time. For example, the rate at which an aeroplane travels is the distance travelled per unit of time, such as kilometers per hour. In chemical kinetics, the rate of a chemical reaction is defined as the rate of decrease in the concentration of the reactant, or the rate of increase in the concentration of the product. Thus, the change in the concentration of the reactants or products with respect to time is called the rate of a reaction. In other words, the reaction rate or the rate of reaction specifies how fast a reaction takes place. Consider a simple reaction in which 1 mole of a reactant A produces 1 mole of product B. Let us assume that the volume of the system remains constant. Initially, that is, at the beginning of a reaction, the concentration of reactant A is maximum, while the concentration of product B is 0. As the reaction proceeds, the concentration of reactant A decreases, while the concentration of the product B increases. Let A1 and B1 be the concentrations of A and B respectively at time T1, and A2 and B2 be their concentrations at time T2. The decrease in the concentration of reactant A, delta A, during time interval delta T equal to T2 minus T1 is given as A2 minus A1. Similarly, the increase in the concentration of product B, delta B, is given as B2 minus B1 during time interval delta T. Using the definition of rate of chemical reaction, we get the rate of the given reaction as a decrease in the concentration of A minus delta A divided by time interval delta T. Now, delta A is a negative quantity since the concentration is decreasing with time. So we multiply it by -1 to make it a positive quantity, as the rate of a chemical reaction is always positive. Similarly, the rate of the given reaction is also given by the increase in the concentration of product B, delta B, divided by time interval delta T. In this case, delta B is a positive quantity since the concentration of the products always increases with time. Hence, we do not multiply the rate of reaction by a minus sign. However, the rate of reaction is not constant. It changes with time. The rate of disappearance of reactants gradually decreases with time as the reactants are consumed. And the rate of the appearance of products increases with time as the products are formed. Hence, the rate of reaction is always taken as the change in the concentration of the reactants or products in a definite interval of time. This is called the average rate of chemical reaction, which is given by this equation. If we plot the concentration of A and B against time, we get the graph shown here. From the graph, we can see that the concentration of reactant A decreases with time, while the concentration of product B increases with time. Note that the change in the concentration of the reactants and products and the time taken for that change to occur, as shown here, depicts the average rate. However, the average reaction rate doesn't predict the rate of reaction at a particular instant of time. To predict the rate of reaction at a particular moment of time, we take an infinitesimally small time period, dt, that is, when time delta t approaches 0, and measure the change in the concentration of the reactant or product during this infinitesimally small time period. The rate of a reaction determined at a particular instant of time is called the instantaneous reaction rate. If the changes in the concentration of A and B are dA and dB respectively, during the infinitesimally small time interval dt, then the instantaneous rate of reaction is given as R instant equal to minus dA by dt or equal to dB by dt. Graphically, we can determine the instant rate of chemical reaction at time t by drawing a tangent at time t on the curves for the concentration of either A or B, and then calculating its slope. The slope of a tangent gives the instantaneous rate of reaction at that particular time. The change on the y-axis divided by the change on the x-axis gives the slope of the tangent. From the graph, the slope of the tangent drawn gives the instantaneous rate. R instant equal to minus dA by dt equal to dB by dt. The rate of reaction may not be same with respect to all the reactants and products. It depends upon the stoichiometric coefficients of the reactants and the products in a balanced chemical equation. Let us consider the formation of hydrogen iodide from its constituents, hydrogen and iodine. The balanced equation for this reaction is shown here. In this case, 1 mole of hydrogen and 1 mole of iodine react to give 2 moles of hydrogen iodide. That is, the rate of disappearance of hydrogen is equal to the rate of disappearance of iodine, and the rate of disappearance of hydrogen or iodine is equal to half of the rate of the appearance of hydrogen iodide. Hence, the rate for this reaction can be written as shown. Let us now consider a generic reaction, where the stoichiometric coefficients of the reactants and the products are different. Let's say m moles of A react with n moles of B to give O moles of C and P moles of D. We divide the rate of appearance of the products and the rate of disappearance of the reactants by their respective stoichiometric coefficients to get the rate for the overall reaction. The rate of chemical reaction in this case is given as -1 by m into delta A by delta T equal to -1 by n into delta B by delta T is equal to 1 by O into delta C by delta T is equal to 1 by P into delta D by delta T. You have learnt about the rate of reaction. Let us now look at the units for the rate of a reaction. If the concentration is in mole per liter, then the unit for the rate of reaction is mole per liter per second. For gaseous reactions, if the rate is expressed in terms of their partial pressures, that is, the rate of change in partial pressure of the reactant or the product, then the unit for the rate of reaction is atmosphere per second.